Good afternoon everybody. So, today we will just continue our third class on coordination compounds. Okay. And here we are just talking about the most important thing for all these coordination compounds is the corresponding coordination number. That means, we are just trying to look at the number of L groups which are surrounding the central metal ion or the metal atom species, which is very important because whenever we write this on a plain piece of paper or on a blackboard, what we see that we write everything very quickly on the board, but the visualization of the thing is sometimes very difficult because it is basically a three-dimensional structure. And if we write nicely this octahedral structure for a coordination number of 6, we find that we can have a typical square plane. So, just we have seen in our previous class that how we can have a coordination number of 4 for say cisplatin, where these two ligands are the ammonia ligands and 2 are the chlorine groups or the chloride groups attached to the platinum center. So, here very simple thing is that the coordination number is 4 based on a typical square plane, and that also give rise to the corresponding theta values for all 4 angles. Now, as we move, which is very important, as we move from a species of coordination number of 4 to a species of coordination number 6, what we can do, we simply bring 2 other groups, one above this plane and another below this plane, which is also true very much if we just know a little bit about the corresponding hemoglobin or myoglobin which is present in our blood. So, in the biomolecules also we have the same situation where this initially formed iron is attaching to 4 nitrogen donor atoms like this. Here we have 2 nitrogen and 2 chlorine groups, but 4 nitrogens from a particular type of ligand, and ligand is a very useful ligand which is a porphyrin ligand. And this porphyrin ligand is very useful in that way because this gives rise to some coordination through nitrogen of a protein chain, which is our globin chain. So, you see slowly in the biological system also how we can develop this coordination part by initially giving a typical square planar ligand, which is the macrocyclic ligand. We call it as a macrocyclic ligand. Then the connectivity towards the protein chain, the globin chain, which is from the protein part, and this protein chain is functioning as a monodentate ligand because it is providing 1 nitrogen from the imidazole ring of the amino acid of the protein chain coordinating to the 5th coordination site of iron. So, slowly we are changing the corresponding coordination number. Initially the ligand is providing 4, then the protein. So, is basically a typically a complex situation where we can have the another site, the 6th coordination site will be available to bind to the dioxygen molecule. What we all know that for the oxyhemoglobin and oxymyoglobin, we consume oxygen for our very survival. When we breathe, we take oxygen from air, and the hemoglobin and the myoglobin present in the blood are getting saturated due to the coordination of this dioxygen to the iron center. So, this typical example gives us all these idea to us that not only a coordination number 6 we are looking at, but also in this particular part the dioxygen molecule, which is a gas like your carbon monoxide, what we have seen in case of nickel tetracarbonyl, that this O2 which is coming from air is also functioning as a ligand, occupying a particular position around the iron center to saturate it for its corresponding property related to that of our hemoglobin, which is oxygenated, that means the oxyhemoglobin species. So, this coordination number 4 is therefore very important, and how we get this coordination number 6, we can see from here that this coordination number, for another example synthetically prepared molecule like this, that we can have the cobalt center having 4 ammonia molecules bound to this cobalt. So, we have 4 cobalt nitrogen bonds and 2 of the cobalt chlorine bonds, and another molecule which is also in the 2 different other geometry, which is the cis form, where the formula is same. Now, both of them are cationic. Cationic means is the cobalt trivalent state, because the 2 other charge is satisfied by the chloride groups. Here also similarly 2 other groups charges are satisfied by the chloride groups. So, this is we are calling as the cis and the trans. So, the knowledge what we know already from your organic chemistry study, that these two will be at 180 degree apart. So, the chlorine cobalt chlorine bond will be 180 degrees. So, they are away from the center. So, they are not 90 degree apart. So, we get a trans situation. So, if we consider this particular square plane and with respect to that particular square plane, what we are just now discussing, that with respect to this square plane, one chlorine is above this plane and another chlorine is below this plane. So, it gives rise to a trans situation that we will see in the case of studying isomerism. But the coordination number, the other one where the Cl cobalt Cl bond is 90 degree, not 180 degree, this is giving rise to the corresponding cis configuration. So, in coordination number 6, we can have 2 situations, one is cis and another is trans. So, that also brings some change in the properties of these 2 compounds. Similarly, for a coordination number 6, which is readily achieved when we get a bidentate ligand. So, a bidentate oxygen-oxygen ligand, that means the O2 type of ligand, which is nothing but when the molecule is shown nicely over here, is the oxalate anion. So, oxalate anion through the 2 charges O minus is giving rise to a bidentate chelation to the iron center, and 3 of them can be surrounding the corresponding iron center. So, it is tris oxalato species. So, tris oxalato species giving rise to a total 6 charge, and the iron is in the ferric state. So, we have a 3 minus negative charge. So, this particular complex part is anionic in nature, which is counterbalanced by the potassium ions. So, we have 3 potassium ions there. So, like that of our hexaamine cobalt 3 chloride, where we charge neutralize with the 3 chloride ions. Similarly, for the anionic complex, we neutralize the charge by means of the presence of 3 potassium ions. So, this situation, so this is the thing. So, there is the 3 dimensional structure will be like this, and this basically gives us little bit some idea. When we draw in a piece of paper, is very difficult to understand that if we consider that this particular metal center and these 2 groups are in the plane of the paper. So, these 2 groups will be above the plane of the paper and the other 2 will be below the plane of the paper. Now, if we realize in that fashion that where the ligand is, then we can have something that is when the bidentate chelation is there. So, if the first oxygen atom of the bidentate ligand is in the plane of the paper or the plane of the board, the second one will go behind. Similarly, if this is in the plane of the board, then this one will come forward, that means it is above the plane of the paper, and in this case one is below the plane of the paper and other will be above the plane of the paper. So, we should have the typical visualization, and this obviously this particular groups, the presence of these groups is telling us, because the oxygens are all red in color. So, this is not the structure of this, but it is something different compound what we discussed earlier also, due to that of your acetyl acetone ligand, which we have seen in the vanadilyl acetyl acetonate one. So, it is tris manganese acetyl acetonate compound, and this nomenclature which is related to the isomeric form, that we will discuss in detail afterwards. And also something we also consider that there is some elongation, because elongation physically what we can consider that when we manganese bound to 3 of the acetyl acetonate ligands, what you see that the manganese is bound to 6 oxygen groups, and if all the manganese oxygen bond distances are not alike, not of same magnitude, so we can have the situation where we can have some of them are shorter and some of them are longer. And if we find that 4 of them are in close range and 2 of them are in the longer situation. So, if we consider that this particular plane is a tetragonal plane, so which is above the tetragonal plane is longer and which is below the tetragonal plane is also longer. So, the nature of the elongation is tetragonal elongation. So, based on a tetragonal plane, one bond is longer and the other bond is also longer with respect to that particular bonds of this manganese oxygen. So, what we find then that this can thus give rise to some isomeric form, the way we have seen the cis trans isomerism. So, how we get these isomers are formed when we can have a octahedral complex and at least two of or more of the different ligands are present. So, if we can have a complex which is ML4 and A2, just now what we have seen that we can have the 2 chlorides. So, we are basically getting 2 ligands around the metal ion. Two types of ligand, one is L and another is A. So, when they are basically giving rise to things, so we can have 2 different compounds. So, this is a clear observation, and that is why these coordination compounds are very nice to handle, that in case of organic compounds whatever we get, most of the compounds are in solution, and if we can isolate they are all colorless and white in color. So, color wise we cannot distinguish these 2 things, but what we see that in this particular case we can have the 2 isomeric form, and if we see that in the same petri dish that one of the isomer is pinkish in color and another is the greenish in color. So, color wise we can also differentiate out that particular color is for one particular isomer and the other color is for the other isomer. So, this is basically we are getting for the left one is the cis tetraamine dichlorocobalt 3 chloride. So, the same compound where the cis compound is pinkish in color. So, tetraamine dichloro compound, but the trans compound which is trans tetraamine dichlorocobalt 3 chloride which is green in color. So, the synthetic methodologies are there and the typical synthetic methodologies can be followed to prepare the cis analog and the trans analog. So, these geometrical isomers, that means the positioning of these groups can also be included while we name these coordination compounds. So, how we name these coordination compounds, which is very easy to know, because sometimes we give the formula and when we read that particular formula is not that the naming of all these things, but we have to utter the name of the metal ion, the name of the ligand, this corresponding oxidation state, and the anionic part or the cationic part which is required for the charge neutralization. So, like that of our simple naming of the simple inorganic salts like sodium chloride, we tell sodium first, that means the cation is named first and then the chloride. So, we call them as sodium chloride. Similarly, for these coordination compounds, the cation is named first and then the anion. So, if we have this K3FeCN whole 6 and CONH3 whole 4 Cl2Cl, this compound we are seeing for last 2 classes, and all the time we are taking the example of these cobalt amine compounds containing some of the chloride groups. So, depending upon the species what is present, so the cations, in one case it is potassium, in another case it is the complex species. But we have to name both of them first, as potassium is the corresponding cation and the complex species is also the corresponding cation. So, this is potassium hexacyano iron 3, which we call the common name of is the potassium ferricyanide. Then within the complex what we see that the ligands are named first in alphabetical order. So, if A, B, C, D, the naming of the ligand. So, we should know the name of the ligand. So, ethylene diamine, when we name ethylene diamine, we consider is that it has A. Then similarly, diethylene triamine, it has D, and when the triethylene tetramine, it has the T. So, the preference in that particular alphabetical order in the names, once we know the name of all these ligands. Similarly, the O for the oxalate group and all other chelating ligands as well as the non-chelating ligands. The name of the anionic ligands end with a letter O. So, letter O is there. So, whereas the neutral ligand is usually called the name of the molecule. So, we do not change the name of the molecule. If it is a neutral one like water molecule, so is aqua. We just simply tell aqua when water is coordinated, when 6 water molecules are surrounding the iron center in some hexa aqua compound. So, we tell them the hexa aqua iron 3. Similarly, when amine groups are present in CONH3 whole 6 3 plus cationic part. So, we know that is the hexaamine cobalt 3 complex part, and similarly the carbonyl part, the carbonyl is also named as carbonyl, which is the corresponding the NiCO whole 4. So, tetracarbonyl compound, the tetracarbonyl nickel 0. But when more than one ligand is present like ammonia as well as the chloride, so we write them with Greek prefixes the di, tri, tetra, penta and hexa. So, when we have, so is the tetraamine, when 4 amine groups are present, we use tetra, but when the ligand itself is having some di part, so we use basically the Greek nomenclature for bis. So, di will be then bis, tri will be then tris, and tetra will be then tetrakis. So, when 2 of the ethylene diamine groups are present, we use the Greek prefixes for bis ethylene diamine, because already the di part is there in the amine. So, oxidation number, next we will consider the oxidation number. So, while we are considering the corresponding nature of the ligand, whether they are charged or not, and the identification of the metal ion will immediately tell us that how the charge is neutralized by looking at the overall charge on the complex species. So, in this particular cationic complex is having one positive charge. So, is the monocatonic complex. So, chromium obviously in the trivalent state. So, this basically we write using the Roman numeral within bracket. So, it will be tetraamine dichlorochromium 2. So, amine A is alphabetical ordering is the first thing, that amine is coming first before we go for the corresponding chloro compound, the naming of the chloro ligand around chromium, which is in the trivalent oxidation state. But when the complex is an ion, we first say that is a potassium, and the anionic part is named as the corresponding 8, ending with 8. So, this hexacyano function is there. So, hexacyanoferrate 2. So, when it is K4 FeCN whole 6, it would be potassium hexacyanoferrate. But if we consider the ion, it would be hexacyanoferrate 2 ion. Similar fashion, in a similar fashion, we will just see that if the corresponding species is present as the corresponding iron as the ferrate, the name of the metal in the anionic complex when 6 cyanide groups are attaching to the iron. So, we are not saying that is iron 3, it would be ferrate 3. So, we write this as the ferrate. Similarly, all other metal ions is changing with the name of the corresponding parent metal center. So, the anions getting that particular nomenclature. So, name of the metal in anionic complex would be, if it is aluminum, it will be aluminate. Likewise, we have seen that if it is iron, it would be ferrate. If it is nickel, it is nickelate, and if it is zinc, it would be zincate. And all these things are very useful for very simple groups attaching to the thing. That means, we have just seen that in case of copper, copper can be in the +2 oxidation state and the copper can be in the +1 oxidation state. And what we see that when we write it as the cuprate, so cuprate can be in the +2 oxidation state and cuprate can be in the +1 oxidation state. So, we should specify that particular cuprate in a Roman numeral of 1 or in a Roman numeral of 2 for the copper oxidation state. Similarly, this ferrate can be for both iron in the +2 and +3 oxidation state, but we will specifically mention the corresponding oxidation number for the metal ion. So, if we consider these are the examples we have taken from your NCERT book, that the typical names, because this is some kind of practice, it is not that this will be asked to you in exam or in some competitive examination also, but how we consider. So, this is some example of say 4 different types of complexes. So, how we read these metal complexes nicely, and when we write this formula, because the formulas are also typically different, here we see that these are the neutral ligand, here we have the anionic ligand, here also the anionic ligand, here again neutral ligand, but it is chelating, and the chloride groups are there outside the coordinate sphere. So, how we write these for its corresponding naming. So, is neutral. So, we do not bother about the corresponding naming, but only that the carbonyl groups are there. So, it is tetracarbonyl nickel 0. So, 4 such carbonyl groups are attaching to that particular nickel in the 0 oxidation state, that simply tell us that the tetracarbonyl nickel 0 is there. Similarly, when we will find again another example from your textbook is the corresponding iron compound, which we are having more number of carbonyl functions surrounding the iron center, which is again in the 0 oxidation state, which is therefore the FeCO whole 5. So, instead of tetra, that would be penta. The second one, if we see that if we do not write the corresponding square bracket, because this will be under square bracket, sodium will be outside the coordinate sphere. So, this one has not been given deliberately, that we should not confuse where it is. So, the cationic part is sodium plus and the anionic part is AuF4 minus. So, is AuF4 minus. So, it is basically a sodium salt of the corresponding anionic complex, which is tetrafluoroaurate. So, tetrafluoro, from gold we get aurate. So, aurate 3, sometimes we also find that it can be aurate 1, that means the gold ion is present in the monovalent oxidation state. So, it is like that of our tetrafluoroborate. This we all know nicely. So, BF4 minus. Similarly, it is AuF4 minus, which is tetrafluoroborate, and it is tetrafluoroaurate. And this already we have discussed it. This is the potassium hexacyanoferrate 3. Similarly, we can have the potassium hexacyanoferrate 2, which is for the ferrocyanide. And the last one is basically the tris complex, the tris ethylene diamine. So, tris is ethylene diamine chromium 3 chloride, like hexamine cobalt 3 chloride. So, it is tris ethylene diamine. So, this function is the cationic part we know is the tris one. So, 3 of the bidentate ligands surrounding the chromium center. So, now in a reverse way, if we understand all these things nicely, in a reverse way, if we write in a running sentence, we basically sometimes write the complex is like this. So, is amine tetraco chromium 2 sulfate. So, when we read it, so reading will also immediately send the message, the signal can be sent to you that we are seeing something, the molecule is like this. So, if you have this corresponding one, that means the amine then tetraco chromium 2 sulfate. So, this particular one what we get, that is not the correct one in this form, that is you have amine. So, what we require for octahedral compound, we require 2 of the amine functions. So, it is not amine tetraco chromium 2 sulfate, it should be diamine. So, amine should be 2 in number, or water molecule should be 5 in number, because you can have some regular geometry which is readily achievable, which we get it, because the penta coordination in this form is not so easy to get for chromium. Because once you get the chromium if can be stabilized in tetrahedral geometry, and immediately it can go to the octahedral geometry. So, once we try to get this sort of corresponding pentanuclear the penta coordination, it immediately attracts the water molecule from the other side to complete it in the octahedral form. But the charge neutralization is very simple, 2 charges from the sulfate ion and 1 charges from the ammonia. So, if sulfate is there, the logic is very simple. If sulfate is there and ammonia is the monodentate ligand, so the number of water molecules surrounding this would be 5. So, the right name would be amine pentaaco chromium 2 sulfate. Then potassium hexacyanoferrate, we have just seen these, all these are example. Likewise, once we know that this naming can also be lead to something to which is cisplatin, that means platinum compound, something is there in cis position, and which is very important as the corresponding one we know that is the corresponding cancer drug. So, we know that the corresponding drug penicillin is also there. So, cisplatin is the proper name because it has been one of the most commonly prescribed as well as the first and successful treatment of many cancer diagnosed. So, this basically gives us some idea that this is the compound where the two positions, that means whether we call about the two amine function and the two chloride functions, they are in cis position and is a coordination number of 4 and a square planar compound we get. Then we just move to the isomerism. What we have just seen, that the two examples we have seen, that we can have a cis compound or we can have a trans compound. So, cis we just now we are naming for this, and similarly we can have the trans platin, but this platin nomenclature is very common name. It is not a IUPAC approved name. So, once we write the corresponding one, the hyphen is not there, is cisplatin. So, correspondingly we can also some idea what should be the corresponding transplatin. So, in this isomerism case, what we see that isomers are there. What is the isomer? We know that they are having same chemical formula, but a different arrangement of atoms. So, only the arrangement of the atoms, we know that the arrangement of atoms will be different if the compound is a cis compound, and if the compound is a trans one, its arrangement is totally different. The way we are just now considering as the two bonds with they are 180° apart and the other two bonds which are 90° apart. So, the bonding which is 180° apart will be the trans isomer, and the bonding which is 90° apart for two similar groups of ligands which are cis isomers. So, we can have two types of isomerism. One can be considered as the structural isomerism. That means, we just looking about a coordination compound, and that coordination compound what we see that this coordination compound have certain coordination number which is directly related to its geometry, and geometry means is 3-dimensional structure, and that 3-dimensional structure will give out something which is a polyhedral arrangement or a polyhedron. As we all know that a particular carbon center, where in methane it is attached to 4 hydrogen atoms, and the geometry is, we all know that is a tetrahedral geometry. So, this is basically a corresponding polyhedral arrangement. So, this tetrahedral arrangement in space where carbon is at the center, we get that polyhedral arrangement. So, once the particular coordination geometry is known, that means the corresponding number of atoms which is surrounding the central part. So, if it is 4, so we can have a particular polyhedral arrangement for this. So, this geometry is therefore is related to the structure. So, the structure of that particular coordination compound, and if there is some variation in all these in related to the connectivity, in related to the coordination nature, ionization and the presence of the solvent molecules, what we will find? We will find something which we can call as the corresponding isomer. So, these isomers we will get for the structures. The different structures what we get here is that once the first one will can be your linkage isomer, that means the linkages are different. So, we should read the name very carefully, that the connectivity is different, we get a linkage isomerism. Then coordination isomerism, that the coordination sphere is different depending upon its position around the metal ion like cis and trans. So, that will come to under the geometry for the geometrical isomerism, but the coordination isomerism, that means something is coordinating and something is not coordinating, that will give rise to the coordination isomerism, and you should not confuse between these two of stereoisomerism and structural isomerism. Then ionization isomerism, nothing related to the stereoisomer, that means the isomers in space and the corresponding solvent isomerism. And this stereoisomerism is much more common and important, and we can mix up these two together. where we can find that the geometrical isomerism is there, and within that geometrical isomerism whether something is showing corresponding optical isomerism or not. So, we have, so this flow chart is very useful to remember also, you can remember it nicely for this flow chart. Why we are talking about these isomers will be having the same formula, but different properties, and we go for the corresponding structural isomers. Then structural isomers, we not only two we have just discussed, is the 4 types, the linkage, coordinate, ionization and solvent. So, this is just the 4 types of this isomerism we can have, and on the right hand side we have the stereo isomer. Stereo means the spatial part, that means the same bonds, but the different spatial arrangements. So, bonds are there, we cannot have the linkage type of thing or the coordination type of thing, but the arrangements are different, like that of your cisplatin and transplatin. Those are geometric isomers because the spatial arrangement is there, and as we have just seen that the corresponding color of these compounds are also drastically different. One was, we have just now seen, one is pinkish in color and another is green in color. Similarly, the another most fundamental property, that means the optical isomerism. So, that basically tells us, okay, color is fine, physically we can characterize one particular compound as the cis variety and the other compound as the trans variety, but afterwards when we consider their application and the other physical as well as chemical or the biochemical aspects, whether we can apply them as some good medicine like your cisplatin. Why cisplatin is only active and transplatin is not, that is an important area of understanding or the knowledge, where we see that only the cis variety has some functionality which can attach to some biomolecule to give its corresponding medicinal value, and that is why it can be used as a very good drug, anti-cancer drug. But the trans is reacting differently, that is why the trans isomers are also different, and a large area of understanding and the research and the work can be there, where we can say that how the cis variety can be synthesized and how the trans variety can be synthesized. So, it is very interesting to note first that how these metal complexes are synthesized, and then particular variety or the particular stereoisomer or the particular structural isomer, how we can synthesize. So, for the other part, that means the structural isomerism, we first see that the linkage isomerism. So, linkage isomerism is very simple to understand, the compound containing ambidentate ligand. So, that also, like side by side we are just talking about the ligands, and we classified the different types of ligands, and whence we say about this isomerism, we see something which we call as the ambidentate ligand. So, so far we are just considering some groups and some ligands. So, one such example we can take first is the N3 minus, which is the azide ion, and we know that is a triatomic anion. So, we have the connectivity of N, N, N and the charge, and the Lewis dot structure you can draw, and you can have how many bonds you can get there with that particular type of arrangement, and the number of lone pairs are there. So, the lone pairs will be available from this nitrogen as well as this nitrogen. So, they can function. So, this nitrogen lone pair can be utilized to coordinate to a bond to a metal, say M1. Similarly, this lone pair can be utilized for bonding to M2. But when we go for a mononuclear compound which could not have any distinction. So, the same azide can be bound to the metal center, whether that particular bond is forming from the left hand nitrogen or the right hand nitrogen, we get the same compound. But if we get the same one where this N is there, so is the thiocyanate is there, NCS, and we have again the charge. And if we just consider that instead of this particular 2 nitrogens, we have carbon and sulfur groups attached to this. So, the overall the total number of electrons are all same, but this charge can move from this sulfur to this nitrogen also, depending upon the lone pair of electrons and the corresponding Lewis dot structure, which is giving us the movement of the charge, that means the residence of the extra electron on sulfur sphere or on the nitrogen sphere. So, now the situation is little bit different when either the nitrogen of the anion or the sulfur of the anion can coordinate to the metal center. So, if we consider that the same, which is also a very good test, the analytical test for identification of ferric ion in solution, in aqueous solution, which is faint yellow in color, and this can be our reagent, and addition of that reagent, this reagent addition to this, which is forming some reaction, which is the change in the color. How you monitor the reaction is very easy to monitor within a test tube or any other reaction flux. We just look at the corresponding change in the color, and this particular color change is due to the corresponding coordination compound formation or the coordination complex formation. So, this particular iron will have the option. So, either this iron in Fe3 plus is coordinating to NCS or it can coordinate to SCN. So, either it can bind this through nitrogen or through sulfur. So, what we are looking for, this particular color change we are looking for, whether we are establishing some new iron nitrogen bond or new iron sulfur bond. And if we are fortunate enough to make both the two compound, in one case we are just going for first coordination, because when it is in water medium we know that it has 6 water molecules surrounding this particular iron center. So, this nitrogen is coordinating. So, this bond, so that will immediately change the coloration, and the color which we get, which is identifiable, is the blood red in color. So, from faint yellow to a blood red coloration will indicate that you have the corresponding coordination of the thiocyanate anion through nitrogen. So, this particular case also give rise to this particular linkage isomerism. If the metal center is bound to nitrogen or the metal center is bound to sulfur. So, obviously, when it binds to nitrogen we get one particular color, and when sulfur is binds to sulfur we get one particular other type of color. And also it is interesting to note here that in some cases when we force it to bind this particular one, the thiocyanate we can bind to the metal center. That means, if we have the copper center, so copper we know that the copper can have two oxidation states, the copper 2 plus and 1 plus, and like the species what we have seen just now, that it can be your 1 minus, the cuprous having bound to 2 chloride groups having a coordination number of 2 already we have seen. Similarly, this particular one, that means this Cl minus can be changed by SCN minus, the thiocyanate groups. So, the binding of these thiocyanate groups can lead us to some groups of this type. So, you can have Cu SCN whole 2 minus if the copper is in plus 1 oxidation state. Similarly, if we go to copper 2 plus, where we can write as NCS and it is 3 minus or 4, which is having a charge of 4 minus. So, this is little bit softer in nature. So, which is soft and which is hard, and that also tells us some idea that among these heteroatoms, the groups which are having different groups. So, nitrogen is harder compared to sulfur. So, the sulfur end will come to stabilize the copper in the plus 1 oxidation state, and nitrogen will come to bind this corresponding compound in the cupric state. So, in this example of this ambidentate behavior of this ligand thiocyanate to bind to the metal center through sulfur and through nitrogen, and when we try to detect the iron in the trivalent state, that the iron in the ferric state which is faint yellow in color. So, this will be the corresponding coordination. That means, since ferric is hard one, which is smaller one also. So, the hard metal ion center will try to attract only the nitrogen end of the thiocyanate ligand. So, it is a linear SCN molecule. So, that linear SCN molecule will try to attract this particular nitrogen center to your Fe3 plus center. So, it is not forming such bond like FeS bond is not forming, instead it can give only the Fen bond through the thiocyanate. Then depending upon the name what we are talking about, the coordination behavior or the coordination or the binding can give rise to one another kind of isomerism. It arises where the interchange of the ligands between the cationic and the anionic entities of different metal ions present in a complex. So, this is one particular compound in which the ammonia groups are bound to the cobalt and cyanide groups are bound to the chromium center. So, you can have certain type of stabilization for this particular thing, that means the chromium can have some good preference for the cyanide ligands instead of the cobalt, which is preferring the ammonia molecules for coordination. Now, if there is an interchange, that means the cobalt will come over here and chromium will come over there. So, that is also a reality when the cobalt is basically going for binding to cyanide groups and the chromium is going there for binding to the corresponding ammonia molecules or ammonia ligand. So, this basically tells us the metal ion nature, the nature and the character of the metal ion, whether the metal ion is present in the cationic part of the complex or the anionic part of the complex, and sometimes it is very easy to understand that if one part of this group, because when we consider that this is there, so it is a reality, you can isolate it out from the solution, you can make it this from the solution, and again you can break it also, because this hexaamine cobalt 3 chloride we know, and the potassium hexacyanochromate also we know, we can make it and we can then put together to get this compound by metathesis reaction or double precipitation reaction. So, in this particular case we can also consider that if we can have that particular one, the environment, and when we consider that this particular thing is also studied nicely for electron transfer reactions, that means this is getting stabilized for both the centers in the +2 +3 oxidation state. But if something is that the one particular center is there and we can look for some electron transfer for the one particular center to the other. So, once we make this particular center to a hard to a soft, its corresponding affinity for the corresponding ligand will also be changing, and we can get something, some intermediate species where one particular ligand like the cyanide, like your azide, cyanide is nothing but your azide, it can bind through carbon and it can bind through nitrogen, it can be a very good bridging ligand in that particular case. Then which is related to ionization. Ionization is always very important and we should not forget that how this ionization can take place when we also consider the corresponding solution electrical conductivity, the lambda m values we can measure, and the corresponding ionization of the metal complexes is important. The way we have seen that in case of corresponding hexaamine cobalt 3 compound, hexaamine cobalt 3 chloride, we have seen that in solution this is present as the trivalent cation and 3Cl minus is present in the solution as the corresponding anionic form. So, ionization isomerism will be available to us if the counter ion in a complex salt is itself a potential ligand. What we have discussed from our very beginning, from our very first class, that the chlorides can be inside the coordination sphere, the chloride as a ligand, it can be inside the coordination sphere or the coordination environment, or it can go outside to balance the charge, or the charge can be neutralized. So, this can be there. So, if the ligand is a potential, potentially you can coordinate to the metal center or you can displace it outside, you can provide something where we get this particular situation where you have the corresponding sulfate group is inside the coordination sphere, in another case we have the sulfate group outside the coordination sphere. So, these two groups obviously we should know the nature of coordination of the sulfate function, and whenever we have some anionic group or the cationic group, always you try to write it down nicely that this has the sulfate function, and sulfate like your perchlorate and having a charge of 2 minus. So, this sulfur is very much saturated, is a tetrahedral one. So, the lone pairs available on these sulfurs will not be available to coordinate to your corresponding metal center. So, that is why we show also the another sulfur bearing solvent, which is dimethyl sulfoxide. So, is a sulfur is there and the oxygen is also there, but it can coordinate to the metal center only through oxygen, because oxygen is the terminal point. Similarly, these sulfate groups can bind to the metal center through this oxygen, and all 4 oxygen can be engaged for binding, but initially since this is a bulky group, it can function as a monodentate ligand or it can function as a bidentate ligand. So, what happens in the first case? In the first case what we see that the sulphate is within the coordinate sphere and already 5 ammonia groups are there. So, for a octahedral geometry around this cobalt center, this sulphate oxygen should function as a monodentate ligand to your cobalt center. So, the cobalt environment is N5O only. Similarly, for the second case, your bromine, we all know that bromine is a monodentate one, and since the cobalt is a trivalent one, so the charge neutralization is taking place from the bromide ion coordinating to the metal ion center as the sulphate so on the outside. So, initially these two can be characterized very nicely because the electrolyte nature is different. This is corresponding thing is the 1:1 type of thing and is 1:2 type of electrolyte. So, the nature of the electrolyte, that means the lambda m values are different. So, capital lambda m values will immediately tell us that you have ionization isomerisms, because the pattern of ionization for the coordination compound is different, producing bromide in the solution and the sulphate in the solution, that can also analytically be identified. If we add silver nitrate for the first case to precipitate silver bromide from the medium, and in the second case barium chloride can be added to separate out as barium sulphate from the medium, and identification of either silver bromide or silver barium sulphate from the medium can also tell us, okay, this bromide is outside the coordinate sphere and sulphate is also outside the coordinate sphere, and these two examples having same molecular formula lead to us for a ionization isomerism. Then solvate, that solvate isomerism is also interesting, where we find that the solvation, that means how many solvent water molecules are present there, and we also call it as a hydrate isomerism. The way we know that the formula of copper sulphate is known as the copper sulphate pentahydrate, that means 5 water molecules are present along with that copper sulphate. So, hydrate isomerism will tell us that whether the water is involved as a solvent, that means as a solvate also, it is similar to ionization isomerism, that the water is coming to coordinate or water is going outside. When water is going outside like this, that means something is there we get, and then some anions, say A2, A3 etc., then some water molecules. So, now since water is not required for charge neutralization or anything, here we can see that these water molecules should be present as the solvent of crystallization, which we are calling it as the solvate, the water solvate. But in another case, these water molecules can come and coordinate to the metal center, where the metal is present in some oxidation state. So, the number of water molecule as solvate would be less, and this water molecule will come to go inside this water coordination sphere, and it is basically a ligand. When it is outside the coordination sphere, it is not the ligand. So, it can have two character. In one case it can be a ligand, in another case it cannot. So, what we see here is that this particular one, the solvate isomers will be therefore find if a solvent molecule is directly bonded to the metal ion. So, if it is directly bonded to the metal ion, we get one composition for the isomer, and if it is outside the coordinate sphere and remain as the solvate of solvate for that particular complex or solvent of crystallization within the crystal lattice, because when we separate it out from the reaction medium, we get some single crystals sometimes. The crystals what we get, they have some lattice, and the lattice is trapping some solvent molecules. So, these solvent molecules are getting trapped even if we do the reaction in some organic solvent like methanol, like ethanol or acetonitrile. Those solvent molecules have also chances to be trapped inside the crystal lattice, but sometimes those molecules can also go inside the coordinate sphere to coordinate to the metal ion responsible for this corresponding complex. Next comes the geometrical isomerism, that means the geometrical isomers, that how the geometry can control the corresponding isomerism for us, and this geometrical isomerism tells us something where we find that a particular arrangement what we have seen and what we have earlier known for the platinum, that 2 of the ammonia molecules we put on the left, and that is at the 90° apart, and 2 of them are in the trans position. So, we get as a cisplatin or the transplatin molecules to us. And why they are so important? Because medicinally we have seen that one can be drug and another cannot be drug, and since it is a platinum bearing metal ion, it can be poisonous to us also, because the elemental platinum as well as the ionic platinum in +2 oxidation state, if not in the +4 or any other oxidation state, is sometimes very much lethal for our survival, for our cell, which can kill cell unnecessarily without damaging the cell when we take this as a corresponding drug for treating the cancerous cell. So, two isomers, why they are so important? Because already we have seen that there will be a difference in the corresponding color. So, this color, this part is very important when we talk about the corresponding transition metal ions, whether it is a 3D, 4D or 5D metal ion. This color can be very useful to know or to understand in all these cases that colors should be different. Already we have seen in other cobalt compound, that is the colors are different. Similarly, if they are solid, their melting points will be different. If they are not solid, if they are liquid, their boiling points will also be different. And their solubility in water, that is very important, that once we get a solid compound in hand, suppose we are preparing both the compound, the cisplatin as well as the transplatin, and we are unable to detect that there is some appreciable color change for them, that there is not basically a very color difference. So, we go for the corresponding checking the solubility, we take certain amount of compounds, say several milligram of those compounds, and put 1 milliliter or half milliliter or some drops of water molecules to it, and we check whether both of them have the same solubility. So, the solubility differences will be there, and the dipole moment. Obviously, we all know that for organic molecules, the cis and trans compound, the some corresponding dichloride compounds, the dibromide compounds, we know that this platinum chlorine bond and this platinum chloride bond, we have a charge separation, and the bond dipoles are there. For cis compound, the bond dipoles will be added in nature, so they are additive in nature, but in trans case it will be cancelling it out. So, the trans isomers in square planar geometry for this platinum, palladium, even in the nickel compound, their dipole moment will be close to 0, or sometimes it is exactly 0 what we theoretically predict. But in case of cis isomer, we have a dipole moment. So, the dipole moment measurement or any other physical characterization technique which can give us some idea about the corresponding dipole values will be useful to identify whether we are having some compound which is in cis geometry or the other compound in trans geometry. And another type of geometrical isomerism which is also very much useful and famous also in terms of the corresponding orientation of the ligands in the corresponding environment, where we are talking about a particular octahedral geometry. So, M is there, and if we consider that this M is forming octahedral compound, similarly this M can also have some ability to form another octahedral compound, where the ligands are, one is A type and another is B type. That means, if we have M and B type, and if they are of equal number, because we have seen, because very quickly you can write it down nicely, that in one situation you can have A4 B2 type, and when it is A4 B2 type we can have cis isomer and we can have trans isomer. Similarly, if the other compound, if it is M A3 B3 type, now the question of trans and cis will not come into picture. So, we can have two orientations. So, if we just see that, if we just simply have this and we just try to write it only, that how we can write it. So, we have to write these three. So, these three, so we can write it as A and B and B. So, this is one particular orientation. So, how we know and how we differentiate this orientation, this is the only thing that you can do. So, this is one ligand, this is the second ligand and this third ligand of one type. Now, we put the same like A here, the same A here, and the third A which we put over here will not put over here, we will put over here only. So, obviously, the B which is occupying this particular position will come over here. So, B is there, B is there and B is there. So, these are basically another arrangement. So, what we are getting basically here is nothing but a particular situation where you see all A's, AMA, AMA and AMA all are 90 degree. So, basically we are getting something which is there. So, it is there in your book also nicely written in this form. So, it is one trigonal face of the octahedron. Similarly, for the other one, the other face, the B face is also is a B face. So, we have a face, all of A, and also a B phase making of all B atoms. So, the isomer like that of our cis and trans isomer. So, it is very much similar because all of them are 90 degree. So, when all A's are there, the AMA angles are all close to 90 degree, then BMB angles are all close to 90 degree, and what we will be getting over there is our typical facial isomer. So, we just get the corresponding facial isomer, that means one face is occupied by these particular A groups and another face is also occupied by the B groups. Similarly, we can get this when we move this thing, that means their A's are different. So, this is particularly the positioning of these A's and the other positioning of B's, and if we consider this A is within a corresponding sphere. So, within a corresponding sphere. So, this is one meridian of the sphere and this is another meridian of the sphere. So, that is why when these are there. So, obviously, this AMA angle, then AMA angle, two of them are 90 degree, but one of the AMA angle. So, one of them, one AMA angle and again one BMB angle, these are close to 180 degree and these are close to 180 degree. We get another situation. So, that situation is opposite to this, like that of our cis variety to facial variety, then the trans variety to meridional variety, meridional, okay, meridional, and we write here abbreviated like cis variety as the facial isomer and this isomer as the mere isomer. So, this type of thing which is very important for the geometrical isomerism, and next day we will start from here continuing something how we can know this thing, because this understanding is very important, because these we are considering as that all A and B are monodentate ligands. Now, what will you do? We do something that where we can have a ligand of bidentate type where one end is A and another end is B, and do not forget that this particular situation you can have also for other situation, that means the bidentate ligand can be AA type and the bidentate ligand can be BB type. So, how you assemble all these things, what are the isomers possible for that and what are the nomenclature for these things are also important, because these sort of things are also there when we go for the multidentate ligands for such as bidentate, the tridentate as well as the tetradentate ligand. Okay, so, these we will all see in our next class. So, for now it is thank you very much.